Okay, so we've talked about how to look at facts about one variable, how to get a sense of summary statistics, mean, median, mode, quartiles for just a single set of data. And the next thing that we're going to look at is relationships between multiple variables. And so the first thing that we're going to look at is scatter plots. So what we're going to talk about is whether or not one variable can be used to make a prediction about another kind of variable. So you have what's called the explanatory variable. This is the variable that is going to explain what's happening. Traditionally in scientific science courses, this is often called the independent variable. Traditionally, this is the variable x. It doesn't have to be x, but if you're thinking of a formula like y equals mx plus b, that is what the explanatory variable is. Or this is also, as I mentioned, called the independent variable. Meanwhile, you have the response variable. This is the one responding to what the other variable is doing. This is often referred to as the dependent variable. And so if the independent variable is x, you might imagine then that the dependent one is y, traditionally. And so the idea is that the explanatory variable is one that you have more direct control over, as opposed to the response variable, which is one that you don't have as much direct control over. So as an example, there's the Fair Isaacs Corporation credit score, the FICO credit score. And so they have a score from 300 to 850. The higher it is, the better credit history you have, which means you pay off your balances promptly and in full, as opposed to paying only the minimum or not paying them at all. And so as a reward for having a good credit history, people who apply for loans can often get lower interest rates if they have good credit history already, because they're viewed as less of a risk. So in this example, the explanatory variable is going to be your credit score. That is one that you have a lot more direct control over. If you buy things with a credit card and then pay off the balances in full, and you do that regularly, month after month, over a period of years, that's going to really boost your credit score. In response to your credit score, the interest rate that you get, that is going to be depending on what your credit score is. You don't have a whole lot of say over what interest rate the bank is going to quote you for an auto loan, but you do have a way to impact your credit score. So if you have a set of paired data, you can graph them as points, and I'm sure that you've done a lot of this kind of thing back in algebra classes. You can have a bunch of x values, and then they will have an associated y value to go with each of them. And you can make a graph, and this is usually called a scatter plot. It's just going to be a bunch of points scattered around the graph somehow. Depending on what it looks like, there are different kinds of patterns or trends that you could find. So for this course, we're mainly going to focus on linear ones. So this would be a linear relationship here. This would have a positive slope because it's going up as you move right. This would also be linear. You can see the points are lining up basically along in a straight line here. And this would be a negative slope because as you move to the right, it goes down. This would not be linear. This actually looks kind of like a parabola. So if you were trying to make an equation, you'd probably have an x squared somewhere in there to kind of get that shape. This is also non-linear. This would be more like a cubic shape where you'd have to have an x cubed term. For this class, we're not going to get into ones that are this complex, but just be aware that lines are not the only option for trying to fit data. And then lastly, you have this where they're just kind of scattered around in no particular pattern at all. So it's possible that there's really no relationship between the data that you are looking at. So if points lie on exactly one line, that would be a perfect linear relationship. In real life with real data, that's probably hardly ever going to happen. I mentioned before, you have a positive linear relation if they have a positive slope. So a positive slope is again going to look like this one here. As you move to the right, you are going up. That is what it means to be positive. If you have a negative linear relationship, that's going to have a negative slope. So then this one where it is going down, that is what a negative slope. That's what a negative slope is going to look like. So we also want to know how to have a sense of how strong, how good of a linear relationship this is. And so to decide how good a line fits the data, we can calculate what's called a correlation coefficient. Now, back in the day, the way that you would find the correlation coefficient is you would do the following steps. You would have to find x bar and y bar, which are the means of all the x's and all the y's. Then you would have to find s of x and s of y, find the standard deviation of all the x's and y's. Then you would have to find the standard deviation of the two of them combined, where you would take every individual x and subtract the mean, and take every individual y and subtract the mean, and you do the mean of the y's with the y's, the mean of the x's with the x's, multiply them together, and then for good measure, add all those things up. And then to top it all off, what you're going to do is take this quantity that we were just talking about, divide it by n minus 1 times the product of the two standard deviations of each of them individually. I have good news for you. Although that is the process by which it is done by hand, we can have the graphing calculator do this for us. And I think you will agree that is much, much nicer. I've actually taken classes where I've had to do this by hand, and oh, Nelly, I mean, I'm good at math and I do it for a living, and I kind of like it, but I don't relish doing such a repetitive and labor-intensive process. Especially when I know the technology is able to do it for me. All right, so the correlation coefficient, the implications here. Based on the way it's calculated, the correlation coefficient is always going to be between -1 and +1. If the value is really close to 1, like 0.95 or 0.89, something like that, if it's close to 1, that is going to be a strong relationship. And moreover, because it's +1, that tells you it'll have a positive slope. On the other hand, if it's a value close to -1, so if you have like -0.95 or -0.87, or even maybe like -0.79, those are all values that are kind of close to -1. And as you might expect, if the R value is negative, that is going to tell you that the slope of your line is also going to be negative. If you're right in the middle, if your value is at 0 or if it's very, very close to 0, that basically means that there is nothing to see here. There's really no meaningful relationship at all. Visually speaking, what does this look like? Well, a perfect linear relationship, the points are going to fall exactly on a single line. This is what an R equal to 1 would look like. Again, in the real world with real data, you're probably never going to see anything quite this neat and tidy. Even if it's a phenomenon such as in physics where the numbers behave in very orderly ways, just through the errors of and variations in how things get measured and the limits of how precisely we can measure things, again, you're not going to see something this neat and tidy with real data in the real world. Now, what you could hope for, this would be really, really good. Getting anything above 0.8 with real world data is actually pretty nice. This is a R value of 0.89. You can see there's definitely a very strong linear trend here. There's a line somewhere along where I'm tracing with my mouse that exists. And so this has a positive slope because as you move right, it goes up. And so this is a strong relationship. This is a more moderate relationship. Yeah, there's still kind of a trend here. You can see along where I'm tracing my mouse, there is kind of a pattern with how these are falling out along a line, but these are much more spread out, and the R for this is about 0.4. So big takeaway from this, if you have a strong relationship, they are going to be packed in tight. If you have a moderate relationship, or a weaker relationship, they're going to be much more spread out. So strong versus weak is basically telling you strong is packed in tightly close together. Weak is they're all kind of spread out and not all that close together. Here's another perfect relation. This is a R value of -1 because it goes down as you move right. This is a negative slope. Again, you're never going to see this with real world data. You might find real world data with like a -0.9 R value. And again, this is going down. The points are packed in very tight. Here, yes, there is kind of a trend, but the points are much more spread out. That would be an R of -0.4. Here's an R value close to 0. The points are all just sort of spread out all over the place, and it's just kind of a hot mess. And then lastly, you've got no relationship whatsoever, at least not a linear relationship. You could probably find a parabola that fits this data set quite nicely. But in terms of being a line, that clearly is not the shape of a line. Lines are not supposed to bend like that. So here we're going to draw a scatter diagram on the axes here. So we're going to plot some points. X is 2 and Y is 4. So let's see, this is 5, 1, 2, and then go up to 4 on the Y. There you go. There is 2, 4. Next we have 4, 8. There's 4. 8 is going to be right about there. Then we've got 6, 10. So here's 6. Go all the way up to 10 like so. Next, we have 6, 13. So we again go to 6. And then we're up at 13, right about there. And then lastly, we have 7, 20. So here's 7. We're going to go all the way up to 20 up here. So that would be what the scatter diagram would look like. And it says label the axes, explanatory and response. So this one is the explanatory. This one, the y-axis, is the response. And then they say, given an R of 0.896, determine if there is a linear relationship between X and Y, and if so, is it positive or negative? Well, this is a very strong relationship. That is very close to 1. So yes, indeed, there would be a relationship. Since the R value is positive, then it's going to be a positive relation. And again, the general trend of these, as you move right, they're going up. That's a positive slope. Let's look at the next example. So here we're going to draw a scatter diagram for these data. We've got 2, 8. So here's 2. We're going to go up to 8, which is going to be right there. We've got 4, 3, which is over here. Then what do we have? We have 7, 9. So 6, 7, go all the way up to 9. We've got 8, 7. So 5, 6, 7, 8. Go up to 7. That's going to be right there. And then we've got 9, 4. So here's 9. Go up to 4. All right, these are kind of spread out all over the place. Again, the horizontal axis, the x-axis is our explanatory variable. The response variable is the y-axis, the vertical one. All right, here they give me an R value, and they say determine whether it is a linear relation. Well, 0.099, negative 0.099, that is a value that is very close to 0. That is not large at all. So this would be no, there is no linear relation to speak of. And again, this is essentially flat. They're just spread out all over the place. There's no real pattern in how the points are falling out on the graph. Determine which of these scatter plots shows the strongest positive linear relation. All right, well, we're going to do these a little bit out of order. This is by far the strongest relation, but the problem is this is a negative slope, because as you move to the right, it's going down. This C is not linear at all. That would make a very nice parabola. We could probably do a nice equation with like an x squared in it to approximate those data. But the problem is this is not linear. So it's not this one. It's not this one because that one's negative. So then this one's positive. That's promising. But these points are much more spread out. This one is also positive. These points are a lot more tightly packed in close together. So the one that is the best answer is this one right here, because the points are going in the correct direction, and furthermore, they are much more tightly packed in together as compared to the other one that is also going in the correct direction. So we're going to stop there, and when we next meet, we will talk about section 4.2 and talk in a little more detail about how to find the correlation coefficient, as well as how to find equations of lines that would actually fit the data that we are looking at.